So I wanted to give you a chance to look at a more complex rate law. So what you don't know is that there's two types of rate laws. What we've been working with is the differential rate law, which has depended upon the concentration. Our next topic will be the integrated rate law, which the concentration depends upon the time. So right now we are working on the differential rate law. Rate depends upon the concentration. So in this example, we have a reaction that has 3 reactants, and our goal is to find the rate law, and I left out the K. So the K is in front of all your concentrations. Our goal is to determine the exponent for each and to determine the value of K, often said the magnitude of K, as well as the units on K. K is the rate constant for the reaction. So there's our initial concentrations. So sometimes you will see this naught or 0 by the symbol, and that just means your initial. So we have BrO3 1-, which is the bromate ion, and bromide ion and hydrogen ion, and our goal is to find our rate law. So we're going to calculate the rate law by determining the orders on each reactant as well as the overall reaction order. The order of each reactant is that exponent, right? So each one has an order of reaction, and then determine the value of the rate constant is the most common way it's called, but it's also the Arrhenius constant. The units on that constant can be complex, so we'll focus on that today. So there's our reaction and our initial concentrations, and we're going to determine the rate law by comparing the initial concentrations with 2 reactions. So my first one, I'm going to look at determining the order of the reaction for hydrogen. So I'm going to determine Z, and I'm going to compare D to C. So when we work out our problems, in chemistry at least, again, I want to focus on D and compare it to C. So we have, I like to write it D over C so I don't get mixed up. Then we're writing our rate for D, which is 160. It's molar per second. So I'm going to write big M over S equals K, and then our concentration, actually I want the actual value of the bromate. Again, I'm looking at D, so we have 0.010 molar raised to the X, and then we have 0.050 molar for bromide raised to the Y, and then 0.060 molar of the hydrogen ions raised to the Z. I'm going to divide it by my information from experiment C. My rate for C is 40 molar per second equals K again. Same concentration for bromate raised to the X. Same concentration for bromide raised to the Y. And the concentration that changed is my hydrogen, and that's 0.030. I recommend that you don't take shortcuts, just do the work so that you get things correct. So let's reduce and solve for our Z. So we have molar per second cancels. My 160 divided by 40 is a 4. My 2 rate constants, K, will cancel. My 0.01 molar for the bromate ion raised to the X can go away because it's exactly the same. For the bromide, 0.05 raised to the Y will go away. We're left with 0.06 divided by 0.03, which is 2 raised to a power. And as you know, 2 raised to the second will give you 4. So we know the order of the reaction for hydrogen is a second order reaction, so raised to the power of 2. So we know that bit at this point. So we're going to look at the order of the bromide ion. So for this one, I'm going to use B and compare it to A. So B over A for me. It doesn't really matter which you put over the other as long as things cancel for you. So my B has a rate of 20 molar per second. My rate A is 10 molar per second. So filling it in a little bit differently. There's my rate constant K. I'm going to put that on the bottom as well. Then my concentration in B for the bromate is 0.010 molar raised to the X power. And in experiment A, it was 0.0050 molar raised to the X. My bromide concentration is 0.025 molar raised to the Y. We don't know that yet. And 0.025 molar raised to the Y for experiment A. And for B, we have 0.030 molar squared for our concentration of H, and exactly the same in our experiment A. So just an aside, if you are given different concentrations, but you know the exponent, so they're not going to cancel. Say we have 0.03 and 0.05 in the denominator for this. You can go ahead and make that a number because they're not going to cancel. So you just work through it mathematically if things aren't exactly the same concentration when you need things to cancel. Anyway, hopefully that makes sense. I'm going to cancel everything I can and reduce down. 20 divided by 10 is 2. Molar per second will go away. My K's will go away. I'm working on my bromate. 0.01 divided by 0.005 is 2 raised to the X. Let's cancel before we solve. 0.05 to the Y will cancel, and our hydrogen cancels because they're exactly the same. So X is the 1 because 2 raised to the first power is 2. So my order of reaction with respect to the bromate ion is a 1. It's a first order. So at this point, we know X and Y. No, we don't. We know X for the bromate, and we know the Z for the hydrogen. So let's work on our bromide. So we know bromate and we know hydrogen. We got to figure out the bromide. Where the concentration for bromide changes is between B and C. So if we compare those two, we should be able to figure out the order of reaction for bromide. So we're going to have C over B for this guy. And my rate for C, I like to put this in so I can find my numbers, 40 molar per second. For B, it's 20 equals K. And my concentration for bromate is 0.010. We know that's raised to the first. I'm just emphasizing that. 0.05. Just make sure you keep your eye on where you should be. That is molar. And this is our Y. That's our goal. And this is 0.030 molar squared for our hydrogen. In the denominator, we have exactly the same for the bromate ion raised to the first, 0.05. Oops, that's where I made my mistake. How about 0.025 molar raised to the Y, and my hydrogen concentration in experiment B is the same, 0.030 molar squared. So once again, cancel and reduce. 40 divided by 20, 2 molar per second. Molar per second cancels, K cancels. My bromate concentration cancels. 0.05 divided by 0.025 will give us 2 raised to the y. Again, y is 1. We'll come back to that in a moment. And our 0.03 squared will cancel. So since y is 1, we know the order with respect to the bromide ion is a first order rate of reaction. So your next step is just to write the law with all the exponents in, and I've included the ones. So your overall reaction order is to add up all your exponents. In our case, it's x plus y plus z. So we have our overall reaction order is just 1 plus 1 plus 2, which is just 4. So it's a fourth order overall reaction. Usually, yeah, I was going to say you put the order there. Fourth order overall reaction order, kind of redundant. The next step is to calculate the true value of K, its constant, and to know the units on that. So that's our next order of business. So taking your rate law for this reaction. So I've written it up at the top. You want to isolate K, and then we can choose any of the reactions, and it will give us the rate constant. So first, let's isolate K. So K by itself is going to be the rate in the numerator, all divided by your concentrations of your reactants raised to their proper power. And I'm keeping those ones in there just to remind you. So that's my equation to solve for K. So now we are going to put the numbers in and solve for it. So K is equal to, and I just took the first one, 10 molar per second divided by 0.005 molar raised to the first. The bromide is 0.025 molar raised to the first. And your hydrogen concentration in A is 0.03 molar squared. So I'm going to go to the next page so I have some room to work, and we'll deal with the value as well as the units. So if you calculate this through, I'll go ahead and write the value here. It's 8.9, and it's a big number, huh? So real fast rate. I have to the 7th. The units we're going to talk about in just a second, all right? But the magnitude of the rate constant is 8.9 times 10 to the 7th. Now those units, it is, we had molars per second, okay, just looking at what we had on that other page, and then we had the concentration of bromate times the concentration of bromide times the concentration of hydrogen squared. So I'm going to do a couple of things. First, we have molarity is really moles per liter, and then there's my seconds. And molarity times molarity times molarity squared is molarity to the 4th. So cleaning this up a little bit, let's change molarity to moles over liters. So now we have moles over liters per second, and this will be moles to the 4th, liters to the 4th. Okay, don't need the parentheses. Now we need to reduce this down, so you have a fraction divided by a fraction. So let me go down here. We have moles per liter per second times liters to the fourth, moles to the fourth. Let's reduce that down, and your liters will reduce the exponent on the liters in the numerator to 3. The moles will reduce its exponent in the denominator to 3. So at this point, we have liters cubed. I like to write the moles first, moles cubed per second. Or this is equivalent, and it's just liters cubed, moles to the minus 3 per second. So your units on your rate constant, K is equal to 8.9 times 10 to the 7th. We have a very large one for this reaction. Liters cubed, moles to the minus 3, S to the minus 1. By using that constant and our concentrations, our rate, the units for rate are always moles per liter per second. That's it.